Right, on to the last leg. It's me again, and I'm going to be running you through the SAP 2012 software. We'll actually be using the software, and I'll be demonstrating it on front of the TV. So before I get started, can everyone just make sure they can see a TV? Some of the detail might be a bit small, so if you're a little bit far away, please take this opportunity to move a little bit closer. What I'll do is run through all the inputs of the software, show you what makes an impact, and also please be interactive. If there's anything you want me to have a look at or change or tweak, please take the opportunity to do so. This is very much a workshop, so if you do want me to look at anything, please just say. Before I get started as well, who has worked with SAP or uses it on a day-to-day basis? Pop your hand up. So we've got a few. Okay, who has come across it and understands it a little bit but doesn't really use it? Okay, that's the majority. And who has never used it and thinks that SAP is something to do with the tree? Good, excellent. Good, right. Just start off, SAP stands for Standard Assessment Procedure. It is, in effect, a big book of calculations. It's government-owned, it's government-produced, and it has been updated over the years. It started off back in 2001, and since then we've had an iteration in 2005 and another one in 2009. And the one I'll show you today is called SAP 2012, which we use to assess compliance with Part L 2013. It came out a year earlier than the approved document. It is a tool for modelling energy consumption in dwellings that assesses space heating, hot water energy consumption, ventilation and lighting. Those are also known as your regulated energy consumers. SAP does also look at unregulated energy consumption, so energy from things like laptops, your appliances, but it doesn't incorporate that into any kind of regulation. So the regulatory measure in SAP is all about energy consumption and ultimately carbon emissions. So we have to do a SAP calculation on a new build dwelling in order to show compliance with approved document L. It has its critics, and I think there's probably a few in this room, some vigorous heads nodding. And I'm sure those who may be nodding might be referring to the Passive House Planning Package being an alternative measure that might be a bit more accurate, and plenty more nods. But it's what we have to work with. It is the industry standard. It's what we have to do to demonstrate compliance with Part L. So, like it or not, it is the tool we have to work with, and it is evolving, like I said. So it hopefully is getting more accurate as time goes on and the iterations go on. So, in terms of the software, there we go. This is it. Like I said, it's basically a book with lots of calculations in. It gets packaged up into a piece of software by different software providers. They will all look slightly different, but ultimately the maths behind it all is the same. So what I'm going to do is actually just talk you through all the different inputs, what makes a difference, and ultimately if you want me to have a look at anything, then I can do that. SAP is a plot-by-plot assessment. So each new dwelling, each new plot has its own SAP calculation. Obviously, if you're building two identical house types and they're facing the same orientation and the same form, etc., they will have two SAP calcs, but they'll probably get the same result. As soon as we start changing any of the building form, orientation, window areas, U-values, building surfaces, anything along those lines, the result we get changes. So this is the software that we've got, and it is, what we've modelled is an end terrace house. It's quite a large house, and the reason I've chosen a large house is that large houses are actually very difficult to show, well, not very difficult, more challenging to show compliance under Part L 2013 than, let's say, a mid-floor flat or a mid-terraced house. Two things just to have a look at and keep an eye on as we run through the process. The first one is down in the bottom left-hand side. If everybody can see just where the mouse is hovering over there, that says TER, and that's target emission rate. That at the moment says 15.4 for this house, and that means kilograms of carbon dioxide per square metre per year. So what SAP will do is work out estimated energy consumption. Depending on what fuel you're using, it then applies what's called a carbon factor or an emissions factor, and that translates your energy consumption to carbon dioxide emissions. Those carbon emission factors are set by the government based on the carbon intensity of that fuel. So, for example, mains gas has a factor that is about half that of grid electricity, which ultimately means that mains gas is a more carbon-light fuel than grid electricity. If we decarbonise the grid at some point in the near future, or in the long future, depending on when that is, then we'll probably all be going back to putting electric panel heaters in our homes because it will be the lowest carbon heat source if we remain if we still target carbon emissions as our overall umbrella in Part L. So we've got a target emission rate for this dwelling, which is 15.4, and then we've got a dwelling emission rate, which is 15.27. Everything is green, so this dwelling is compliant with Part L 2013. For carbon emissions, there are obviously different criterion in Part L as well, but this is one of the main ones. Just alluding to what Ross was saying a little bit earlier about moving towards measuring energy consumption instead of carbon emissions, at the moment we're measuring both under Part L 2013. And the ones to look out for here are up in top right-hand corner, just next to where it says compliance check in green. We have two four-letter abbreviations, and the first one is target fabric energy efficiency. That says 57. And the next one is dwelling fabric energy efficiency, which says 50.1. So we've got a tuffy and a duffy. Now, those are our measure of energy consumption, or our space heating demand. It's kilowatt hours per square metre per year. So, in order to comply with criterion 1 of Part L 2013, you need to ensure that your dwelling emission rate is below the target emission rate, and your dwelling fabric energy efficiency, it doesn't roll off the tongue, is lower than the target fabric energy efficiency. And those two things will change depending on the build form and the fabric specification, ultimately. So we need to show compliance with both of those. So, onto the software itself. What we have here is a Build4Quality sample house, and then you can see down the left-hand side all the different inputs. So, dimensions, opaque elements, openings. I'll take you through all of those, show you the inputs. We can play around with a few things and see what the impact is. This is an end terrace house, so ultimately we do, and it's quite a big end terrace house, so we do have quite a lot of heat loss from this home. That means if we start playing around with anything that influences the heat loss in that building, that's probably going to have the biggest impact on our overall results. And we'll run through that in a minute. So, the first page I won't really go into very much, it's mostly administration. The only thing that will make a difference is the location. So this house is in the Thames Valley. The only areas that influences is summer overheating, and if we had air conditioning or comfort cooling, it would influence that as well. Location in SAP doesn't currently influence your heating demand. That's obviously one area where it could become a bit more accurate in the future. So, if we start running through the software, the first bit to have a quick look at is the dimensions. What we need to start doing is building up an image or a model of this house so that we can start to assess heating demand, lighting demand, etc. It is a 4-storey house with a room in the roof. Each floor is approximately, well, what have we got there? 47.68 square metres to be absolutely precise. And then we input in floor-to-ceiling heights. So when we've done that, we've built up the volume of the house. Now you'll notice that SAP is only looking at this in regards to the whole house. We're not breaking it down room by room, which is something you have to do in the non-domestic equivalent of SAP, SBEM, or what you'd also do in dynamic simulation modelling as well. So you can see we're looking at the whole house. We do have to lift off the living room area because SAP assumes that the living room is heated to a slightly higher temperature than the rest of the property. Whether that's accurate in real life or not, that's probably up for debate. So at the moment we've built up this volume that we need to heat. We then need to figure out in that section, in this section, opaque elements, how much heat loss have we got from this box, this visual box that we've got. So we need to specify heat loss for our ground floors, external walls, and our roofs as well. SAP considers heat loss to be any area that is adjacent to another area where the temperature is lower, in effect. So what you'll find is if we are, let's say we're talking about a flat over a retail unit, we ultimately assume that into the retail unit, that floor or that ceiling separating the two would be heat loss because that retail unit will be heated at different temperatures to different times of the day to the property. So we need to apply heat loss values. So we've got a ground floor here, 47.68 square metres, obviously same as the floor area. And that's, in this case, it's got a U value of 0.15. It's very easy in SAP to just put a number in there. I could put that in as 0.001 if I wanted to. But obviously, we need to make sure that can actually be built. So the software does have an inbuilt U-value calculator, but we need to make sure, and it's our responsibility to do it, that whatever values we're assuming here, we need to be informing the design team of those. We need to be talking with the architect to make sure they are actually achievable. So that's our ground floor. Next one we have is an external wall, and the U value there is 0.18. that is the same value that gets assumed in what SAP calls the model design. Now, the model design is basically the specification it uses to work out your target emission rate. So what we're saying here is that what we're proposing to do with the external wall is exactly the same as what SAP is assuming when it works out our target. So we're not being penalised, but we're not getting any benefit either. 0.18 in masonry construction, probably 340 mil width, something along those lines. And then onto the roof, we have two different U values here. We've got a flat roof and then also a terrace in this property, and we can split that out and apply different U values there. So those are our fabric U values. Just to give you a bit of an indication, if, for example, we went down to 0.15 on our external wall, remember it's probably it is the biggest area of heat loss we've got in this property. We are improving the result by, what's that? It's about 1.8%. So it's not actually a huge difference, but it does start to chip away. And you can see as well up here, the dwelling fabric energy efficiencies come down. It was 48, it was 51, now it's 48. So we've got to balance those two. Another area that was introduced under actually Part L 2010, so the previous iteration of the current building regulations, is party wall heat loss. And this came about due to some studies that I think were conducted by Stanford Brook University, I think, yeah. And they were looking at party walls in terraced houses, and those party walls were empty. They weren't filled with any insulation, and they found that the U value, the actual heat loss from those party walls, was about 0.5, maybe 0.6, something along those lines. So there's a lot of heat loss we were ignoring effectively. It was convective heat loss. Heat was going into the cavity between two homes and rising out into the roof and out into the atmosphere. So we now have to assess party wall heat loss. And it's not like a normal U-value calculation. So we don't look at the makeup of all the different materials. We don't look at the thermal conductivity. We don't really change the nature of the insulation to get a better result. We have a few different drop-down options, and they are very straightforward. If you have a solid party wall, which we don't see too often, but you can build them and you can comply with the acoustic requirements of Part E, that would achieve you a U value of 0. And the reason for that is you have no cavity and there's no convective heat loss. We're not talking about heat transfer here. It is convective heat loss. The building regulations minimum requirement is that you achieve a U value of 0.2, and that can be achieved by effectively sealing the cavity. So we're ensuring that we're not really getting any airflow in that cavity. You don't have to fill it with insulation, but you can seal it. If you had a U value of 0.2, you will find, yes, you are compliant with the limiting U value, but actually you're going to really struggle to comply with the overall carbon target. And I'll show you that now. If I change it, you can see, one, we failed, and two, we failed by quite a long way. The reason for that is this is a obviously relatively large party wall area that we're dealing with, but also when SAP works out your target emission rate, it assumes that if you have a party wall, it will achieve a U value of 0. So you're effectively being penalised if you don't fully fill your party walls. I think a point up for discussion at the moment is whether you consider there will be any convective heat loss in party walls in apartment blocks, where you might be actually having a concrete floor above that party wall. I think that's an area that's up for grabs at the moment. So that's party wall heat loss. That is big influence and something we need to be looking at, and obviously balancing Part E as well. I know quite a few of the robust details do allow for full fill insulation there. Quick nod to thermal bridging. I talked about it earlier. I said it's one of my favourite topics, which is probably quite boring, but ultimately what we have in SAP is a list of all the available junctions that we have in a property and what the psi value is for those junctions. So you can see in this property we've got a total length of all the lintels. They're coming in at 22.25 metres. They are all given a psi value, in this case of 0.3, and that psi value has been lifted from the accredited construction details. So that, in effect, is an industry good practice detail. What we do know is that there are some other details that are better than that. A lot of the time, if you actually go to the effort of modelling the detail yourself, you will show an improvement simply because the accredited details are a little bit conservative. Alternatively, you could take a completely different approach and have maybe split lintels, or you could have reinforced plastic lintels. Those are both options that would give you very low psi values. But let's just say if we calculated a psi value, and if we achieve something like 0.22, which is entirely achievable with a standard construction, if we did that, if we have a look, we go from 2.6% to 3.3. So actually, thermal bridging is a very big impact on the calculation. That's only one junction that we actually looked at. Granted, it was the junction that has traditionally the highest heat loss, but it is certainly worth addressing your other junctions where there is heat loss. And it's, again, improved the fabric energy efficiency. What I would say that thermal bridging is, if you look at a property in terms of where proportionally do you lose the most heat, when we start improving our U values and they become very good, proportionally the amount of heat we lose from thermal bridges increases, and it can increase quite significantly. So that's why it's important that we do start addressing it and really pushing forward what we're doing with thermal bridging. So that's our opaque elements. So we have our volume of house. We figured out how much heat loss we have from it to a certain extent. We then need to specify what openings we've got. And in SAP, we have to look at doors, windows, and roof lights. With windows, give you an idea of what can have an impact and what will have an impact. Obviously, orientation is a big one. If you've got a south-facing window, you're going to get a lot more solar gain. That'll reduce your heating demand and potentially make it easier to comply. A couple of things down the bottom here, just to be aware of. Got a G value. A G value, or a G factor, it's the amount of solar radiation that comes through a glazing system. The lower that figure, the less solar radiation you get. That's one of your primary means controlling a risk of summer overheating. There are some SAP defaults that can get used. 0.63 is the standard default for double glazed unit. In reality, you might find figures are going to be lower than that for potentially glazing systems in homes. For apartments, especially single facade apartments, you may well be getting down to the realms of 0.3, something along those lines. It does have an impact on the aesthetics of the glass as well, so that is something that needs to be weighed up. It is very much something that needs to be looked at on a project-by-project basis to make sure that you're not going to be demonstrating too much of an overheating risk. And then obviously the U value, so how much heat are we actually going to lose from this window? U value here is 1.3 at the moment. The notional value used to work out the target is 1.4. I think it's probably safe to say you could get down to 1.3 on double glazing systems. If you start going much lower than that, I think you're probably moving into triple glazing. Obviously increases the cost somewhat. So I have to model all of our windows, taking into account the orientation, glazing area, and G value. That's very important. So we're then moving on to ventilation. And in SAP, we've got two types of ventilation that we model, uncontrolled and controlled. I'll start off with uncontrolled, because that's the easiest one to show you. That is effectively our air permeability, so our air test. So what we do in SAP at design stage, we will enter in a figure that we believe to be achievable. So that might come from past experience with a developer or a contractor. It might be down to potentially a target. If it's a passive house, then, well, we need to be achieving a much lower target. Also, if it's passive house, you wouldn't be using this as the primary modelling tool. It would be the passive house planning package. But we'd enter in a figure. In this case, it's 5. Now, what this means is, in this site, we would either be air testing every dwelling on site and achieving a figure of 5 or less, or if we weren't air testing this property, and we're only air testing a selection of dwellings across the site, we have to absorb what's called a confidence factor for those units that aren't tested, and that's a figure of +2. So what that means in this case, we're either testing at 5 across the board, or if we're not testing everything, we need to test a selection of units and achieve 3 or less to allow for this +5 figure. It can have quite a big impact in SAP once you start getting below from 5 to 7. So if we go to 7, let's just say we're not quite as good at air leakage testing and we're a bit leaky, it fails. So for actually what can be considered to either air test everything and pay a little bit of attention to detail on site, we found a way to comply with Part L. Ooh, excuse me. Going much below 5 will have an impact, but it will change depending on the ventilation system you're using. So if we changed at the moment to MVHR, once we start getting down into the realms of 3 and 2, that system becomes much, much more effective and more efficient because we don't have a leaky property. And then we start to see some big benefits there. But if we leave it at 5 for the moment, we've then got our controlled ventilation strategy to think about. And under Part F, mentioned a bit earlier, once you go below 5, you need to increase the background ventilation rate that you need to achieve. That can be challenging to do with System 1 ventilation, which trickle vents and local exhaust. So you might have to move to System 3, continuous extract. It reduces the amount of trickle vents that you need. You do still need some. And in some instances, it will give you an improvement over the use of System 1 in this calculation. If we move to MVHR, that again can have a more positive impact, but that does vary depending on the size of the house. Tend to find MVHR in a very big house will actually give you a worse result in SAP, simply because the system uses quite a lot of energy in terms of the SAP model. Whether that reflects, again, as-built performance, and that's another question, and I think SAP as well only focuses on carbon emissions and energy consumption. We're not talking about occupant comfort here, which is something that MVHR can improve. Just a quick nod to what's called the Product Characteristic Performance Database. That is a database of lots of different systems within SAP, and effectively if you have a ventilation system, a heating system, potentially things like wastewater heat recovery, which has been mentioned earlier, but I'll come on to in a minute. It needs to be modelled and tested for us to be able to use it in the calculation. So we do come across some very innovative and potentially very effective ideas, but we can't model them unless they've been approved by BRE testing to go into this calculation. So that is one thing to watch out for if we're looking to push forward a technology that isn't yet in SAP. It can be done. There is just a testing process to go through that, with a lot of things, costs a bit of money, but equally, if the technology is good and robust, it can then be incorporated into the modelling software, and then we can start reaping the benefit in the calculation. So, on to heating systems. SAP is relatively flexible here. There are some heating systems we can't model, but in the main, we can model the majority. So, obviously, mains gas, that's what we've got in this instance. We have a boiler that's selected from the database down in the right-hand side. But if we wanted to, we can model oil systems, electric systems, heat pumps. We can also model it if you want to get your local chippy to give you all of their used oil, and you can actually model that as well in your oil boiler. Future of zero carbon is for us all to eat fish and chips and use the leftover oil. Apparently, it is zero carbon in SAP. So SAP's trying to get ahead of itself. We have got a few options there. Heating controls are obviously very important. How efficiently is that property being controlled? Again, SAP is looking at the whole property as opposed to splitting out different rooms and having different heating systems. At the moment, this property's got twin zone control, time and temperature zone control, so you've got two independent piping circuits, certainly with a gas boiler system anyway, and those are both independently time controlled and temperature controlled, so they can come on at different times of the day. We can also model secondary heating systems, secondary main heating systems. So if you have two different heating systems in a property, that can be modelled. And then again, we can also model what we might refer to as traditional secondary heating systems. So that would be things like a wood-burning stove or potentially gas fires, something along those lines. When we do that in SAP, it assumes that that accounts for 10% of the energy consumption in that property. So if you install a wood burner, wood being a zero carbon or near zero carbon fuel source at the moment, that will give you quite a positive impact on the calculation. If you went for a gas fire that's not as efficient as your main heating system, that's going to make the result a little bit worse. Can also specify a cooling system as well in SAP. So if you are using air conditioning or comfort cooling, it can be modelled. It will have a negative impact on the calculation simply because the target emission rate doesn't allow for it. So SAP's assessment of summer overheating assumes that we're using passive measures. It doesn't allow for any kind of comfort cooling. Likewise, so does the target emission rate. So if we did have, let's say it's an A-rated, energy efficient, what's the area of this property? Let's say it's 150 square metres, let's go for something like that. It's made the performance of the calculation slightly worse by incorporating a comfort cooling system. It actually hasn't, it's not made it that much worse. So you tend to find that sometimes it might not be as much of a negative impact as you might think it would be. So that's our heating system. Next, we've also got water heating to have a look at. Now, obviously, in a lot of instances, your water heating is going to come from your main heating system, so gas boiler. In this case, we've got a regular boiler, so we've got a water cylinder. We also have to specify the loss factor from that water cylinder. I won't go into the details around this, but basically this isn't one example of where communication within the design team is really important, because this has quite a big impact on the calculation. I can assume something in terms of cylinder loss. I need to inform whoever I'm working with that that's what I've assumed, so they can make sure that they're specifying a product that meets that standard. Alternatively, I need to make sure I'm recommending something that's actually achievable. So it's what I'm coming back to saying, it's very easy to change numbers on this screen. They've actually got to be workable solutions. That's figure there is taken from manufacturer's catalogue. They do have all that data readily available. So it's just about being really open with what's actually been put in the calculation to make sure that we're not going to run the risk of any issues. Got a presentation coming up on the performance gap, and I think this is one of the areas that really needs to be tightened down to make sure that the homes we're building do actually match design performance, notwithstanding all the other issues that we need to be talking about on that one. Solar thermal systems, we can be assessing solar thermal systems where you are feeding hot water from sun's radiation into your water cylinders. That will have a big impact in a property where you have quite a high hot water demand. In a property that's got a relatively small hot water demand, solar thermal won't make much of a difference and may not be cost effective. So again, we've got to track back to where is the most energy being used in this property. And then, so, yeah. Let's take into account occupancy. SAP makes assumptions on occupancy. So if I have this home here, which is, I've forgotten how many square meters, a couple of hundred square meters, SAP assumes it will be occupied by a certain number of people. We don't have any control over that. So that's, if you're building, if this was a one-bed home that was 200 square meters and it was a big open plan, the water heating demand would be exactly the same in SAP as if this was a 5-bed home. So you do find that it's just a flat assumption. We don't have any control over that.
Why? Probably don't know the answer to this. Why have they done that? Why haven't they added in?
I think there's two things. One is to have a consistent approach. And I think the second thing is that if you have to start, from an enforcement perspective, if you have to start regulating every single input that goes into the SAP calculation without the appropriate audit process in place to really tighten up on that, you open up a bit of a minefield. It would be very easy for me to change lots of occupancy patterns and potentially hope no one would notice. So that's the risk. This is government software, and they want a standardised approach, I think, at the moment. That could well change. And you could easily introduce an approach that it is very obvious where alterations have been made to standard convention. I think that would be the way to go. So that was solar thermal panels. That is one means to reduce your carbon emissions and energy consumption. Will have a much bigger impact in a home where your hot water demand is higher. The next one, a couple of 5-letter abbreviations. Sorry, I had to count them. This is wastewater heat recovery system, alluded to a little bit earlier in the presentation. Wastewater heat recovery, relatively simple technology. In fact, it's incredibly simple, where you effectively just have twin skin pipe where you are recirculating heat from outgoing shower water, feeding that back into a cylinder or a boiler. So the water coming into your cylinder, or going into your boiler, is potentially about 30% higher temperature than it would be if it was coming straight in off the mains. Obviously reduces your energy consumption. It doesn't recirculate your shower water. I have heard a few people express concerns on that. It's just the heat. But in this property, we have a reasonable water demand here, so it's actually made quite a big improvement. It's been about 7% in this case. Now, for cost-wise, I think they're about £500 to £700, something like that. It can add up, and it can be a way to start chipping away at the regulations. That's wastewater heat recovery. The next one here, same principle, flue gas heat recovery. Can either be a bolt-on box that recovers heat from your exhaust gases on the flue, or it can be an integrated unit into the combi boiler. Either way, principle's the same, recapture that heat, feed it back into the boiler. And that is something that equally can have an impact on the calculations depending on energy demand, etc. Not quite as big, about 3%, depending on the size of the property. Again, relatively simple technology. So this tab here, this is where we'd enter in our renewable technology, either valuable on-site energy generation or eco-bling, depending on which side of the fence you are on these things. But we have the ability to assess photovoltaic panels, so generating electricity from the sun's light, sun's radiation, and also micro wind turbines. Has anybody ever worked on a project with a wind turbine? Yeah? Excellent. How did it go?
Sorry, I just don't think I'm used to that word. You'll see it on the signal when we built at the BIE Innovation Park. Some people might remember that.
That's
Years ago, and it was the biggest disaster at times.
I think it's possibly for that reason. I don't want to tar the whole industry with the same brush, but very few and far between, I think it's fair to say. You can see a couple out of this window if it wasn't so foggy. There's one on a tower the St George's Tower, and there's also one on Strata 1, which has got the 3 wind turbines in the roof. I don't think they're ever turned on because they made the penthouse vibrate, apparently, so that's part of the problems you might have there. Photovoltaics, much more common solution, and something that we're seeing a lot to demonstrate compliance with the London Plan. The London Plan, as we heard earlier, sets a requirement for a 35% reduction in carbon emissions over the requirements of Part L 2013. If, and this may not be the be-all and end-all, but if we decided that we were happy with this building fabric and we didn't want to make any other changes to it, and we wanted to achieve London Plan compliance, we'd be looking at a PV array of about 2.5 kilowatt peak, so that's 10 panels, which is a reasonable size PV array. You might not be able to fit that on the roof. Certainly, if you have any overshading issues, room-in-roof properties where you've got dormer windows, Velux roof lights, that's obviously going to limit your area. And it might be that you just can't fit enough panels on to achieve the target. So it's definitely, it can be a challenging target to achieve on large houses, absolutely. So that's our renewable energy section. And then last but not least, we have this little tab down here, which is overheating. I talked about Appendix P a little bit earlier in terms of it being possibly a constrained assessment of summer overheating. It takes into account overall air change rates, depending on whether we can get cross ventilation through the property and how much we can open the windows. Now, we have to be obviously concerned about security. We can't say that the windows will be open 24 hours a day if you have a ground floor flat, because chances are someone will walk in and take something. So we have to be realistic. We also need to be aware that if you have a property that's adjacent to a main road or where there are any kind of noise or pollution issues, you're not going to be able to open the windows, and that feeds back into whatever your ventilation strategy might be. If that was the case with this property, we're now going to flag up an overheating risk because we're not getting the ventilation through the property to purge any excess heat. We would now have to go back and start looking at the G value and bringing that down, or incorporating some kind of solar shading, or possibly look at changing the thermal mass. Now, obviously, if we've got a product, we're picking up a project that's actually well into concept, well into design stage, we're not going to have as much flexibility on making these changes. So we do need to be addressing these types of things quite early on in the process. Yeah, there we go. Windows open half the time, so effectively saying here, when the occupant's in the home, they're keeping the windows open to ensure they're getting the purge rate of ventilation. We can include ventilation rates from MVHR systems, so if you have, and you tend to need quite a large MVHR system, you can sometimes achieve the air change rates you need with an MVHR system, just in terms of moving air through the property. And then last but not least, pretty much commonplace now, but low energy lighting. The building regs regulations requirement is 75%, so 75% of all your fittings need to be low energy. If you did that, it actually makes quite a big difference on the calculation. Nearly fails. So for the cost of however many it might be LED bulbs, if you're in pushing it towards the top end of the market, or just compact fluorescents, then it's a relatively quick and easy route to compliance. So that, in a very quick nutshell, is SAP and all the various bits and bobs that we have to enter. There can be quite a lot of detail behind it and quite a lot of chopping and changing of specifications. I think the important thing for us is to make sure that whatever assumptions are being made, one, they actually work. Well, that's obviously really important. But secondly, they're communicated effectively. That really is vital to make sure that, well, one of the steps to reducing the performance gap, which I think we'll hear a little bit more about in a few minutes. So I have approximately 3 minutes left. Does anybody have any questions, or is there anything you'd like me to demonstrate on the software? No? Okay.
Sorry, just one.
Yeah.
You mentioned G value. Can you have your input in external shading factor?
Say that again. Sorry, can I input it? Yeah.
External shading, right?
Yeah, so, where's my mouse gone? There we go. So, in openings in SAP, we have this area here where we can look at overhangs. Now, obviously, if, at the moment there's no balconies. If we had a balcony above a window, then we would measure that in terms of the width of the balcony and also the overshading. You could do the same with brise-soleil, something along those lines. So we can model it. It just doesn't get modeled to the same level of detail that you might do in dynamic simulation modeling. Okay, so on that basis, just to finish up, just a couple of little takeaways. One, when we're looking at SAP and trying to get compliance with Part L, make sure we focus on the areas with the highest energy demand. That's where you'll get the biggest win in terms of making gains in the calculation. ensure all the assumptions are correct. Really important, you've got a design team rigor. You need the M&E guys to be checking the M&E services that have been assumed. We also need to be making sure that when we're calculating U values, we're assuming the right number of wall ties in the if it's masonry construction, or assuming the right timber ratio if it's timber frame. These things make a big difference, and they do contribute to the performance gap. Engage early. SAP is not a design tool. It is a compliance tool, by which I mean you use it to show compliance with the relevant regulations. However, it can drive your design and it can change your design. So it's important that if you need to be doing that, we want to be making those changes as early as possible. Thank you. Okay, Scott, changing.
Best presentation I've ever heard.
Thank you.